Hello everybody, Mr. Odom here, and today we're going to talk about independent and dependent events, section 10.5. I highlighted the stuff you need, the usual stuff, your pencil, composition book or notebook paper, and a calculator. The learning target for this video is I can identify independent and dependent events and use formulas to find probabilities of independent and dependent events. So let's get started. So compound events, which is what we're talking about, they may be independent or dependent. So you're going to want to write this definition down. Independent or events are independent if the occurrence of one event does not affect the likelihood that the other event or other events will occur. Okay, and there is a formula to find the probability of independent events. So if I want to find the probability that A and B take place, those are my events, and if they are independent, then all I have to do is find the probability of one, the probability of A, and the probability of B separately, and just multiply them together. This also doesn't matter how many events you have. So here, A, B, and C, I would just find the probability of A, probability of B, and the probability of C if A, B, and C are independent events. That one of them happens, and that does not affect the likelihood that the other ones will happen. So we'll go ahead and pause the video here so you can write down this definition of independent events, and then I want you to write down the formula. Okay, so the video will pause now. All right, so we're back. Let's see how this works. So you spin the spinner and you flip the coin. What's the probability of spinning a prime number and flipping tails? The first thing to notice is that these are independent. I can't spell independent and talk at the same time. These are independent events. Spinning that spinner has no impact whatsoever on whether you get heads or tails. And whether you get heads or tails has no impact whatsoever, does not affect the likelihood that you would spin a 1. Okay, so these are independent events. So the probability of spinning a prime number and getting a t is the same as finding the probability of spinning a prime and multiplying it by the probability of getting tails. So the probability of spinning a prime number, well, you have to know what the prime numbers are. They start with 2, and then 3, and then 5, and then so on. So 2 is the first prime number. So there are 3 out of the 5 numbers that are prime. Flipping tails, we flipped coins before. We know the probability is 1 out of 2. We just multiply those together. There's no canceling I can do there, so I end up with 3 out of 10 or 30%. So the probability that you would spin a prime number and flip tails is 30%, which is very close to 25%. So it's unlikely that you would do that. Okay. Let's look at this problem here. What's the probability of spinning a multiple of 2 and flipping heads? Well, the multiples of 2 would be 2 and 4. So I want to find the probability of spinning one of those 2 and getting heads. So all I do is break it down. The probability of spinning a 2 and a 4, a 2 or a 4, multiply that by the probability of spinning heads. So getting a 2 or a 4 on that wheel, there's 2 different favorable outcomes out of the 5 possible outcomes. We already know about flipping a coin and getting a tail. So I multiply that together. Was there canceling I could do here? Yeah, sure there was. I could cancel the 2. So I end up with 1/5, which is 20%. So this is even less likely to happen than the first one of getting a prime and flipping tails. Okay. independent events. They can take place and they don't affect the other events. All right. Dependent events, that's different. So dependent events are events, well, let's see, events are dependent events if the occurrence of one event does affect the likelihood that the other event or events will occur. And that effect to the likelihood could be very small, but it will affect it. Okay, so let's see what we're talking about here. The formula for the probability of dependent events is the probability of A and B taking place if they're dependent, which means maybe B depends upon A, is I find the probability of A, and then I find the probability of B after A takes place. Okay, so after A takes place. Let's look at an example. So you got people randomly chosen to be game show contestants from an audience of 100 people. So I've got 100 people, that's what I'm starting with. And you're with 5 of your relatives and 6 other friends. So you want to find the probability that one of your relatives is chosen first, then one of your friends is chosen second. So what would be the probability that your relative would be chosen first? Well, there are 100 people in the audience. 5 of them are your relatives. So this would be 1 out of 20. So there's a 1 in 20 chance, which is a 5% chance that one of your relatives would be chosen. Now, what about for the second choice? So we've chosen, let's say we've picked one of your relatives, then what's the probability that that one of your friends is chosen? Well, that's going to be a little different, all right? Because there aren't 100 people anymore to choose from because we already picked one of your relatives. So how many people are there? There are 99, okay? So the likelihood of this event taking place was impacted because we chose one of your relatives first. And how many of your friends are there? 6 out of 99. And we can go ahead and simplify that, divide everything by 3, and we get 2 over 33. So what is 2 divided by 33? We get about a 6.1% chance. So notice when I chose one of your relatives, the percentage went up to how likely is it that you could choose one of your friends after a relative was chosen. So it increased a little bit, okay, because we are choosing from 99 people instead of 100. All right, now find the probability that this compound event happened, that one of your relatives got chosen first, and then one of your friends got chosen second. All I do is take these probabilities and I multiply them together. So I have 1 over 20 times 2 over 33. And that's the probability from there. That's the probability from there. And is there canceling? Yes. That can be a 1. That could be a 10. So there is a 1 in 330 chance that a relative would be chosen first, followed by a friend. And 1 divided by 330 is an extremely small percentage. It's about 3%. Okay, 0.3% chance that one of your relatives would be. Okay, let's look at another problem here. So what is the probability that you, your relatives, and your friends are not chosen to be either the first or the second contestant? Okay, so let's look at this. So the probability that group, I'm going to put you all into a group. How many people are in that group? Well, you have your 5 relatives, your 6 friends, and don't forget yourself. Okay, so that's 12 people to choose from. And the probability that neither one of those 12 was chosen first would be, well, how many people are left? There's 88 out of the 100. So there's about an 88% chance that you and your relatives and friends are not going to be chosen first. What about they're not chosen second? Well, so someone was chosen first. It just wasn't anyone in your group. So again, there's 99 people left. And out of the 99, you guys make up 12. So I have to subtract that, and that gives me 87. So I figured this probability out, and it's 87.87%. I'm sorry, 87.87 repeating percent, or 29 out of 33. Okay, and this one was 22 out of 25. So if we want to find the probability that no one in your group was chosen first or second, we just multiply the probabilities together. There's the first and second choices. You guys aren't part of that. So I multiply them together. You see that I can cancel here. 22 and 33 are both divisible by 11. I end up with 58 over 75, which is approximately, or actually exactly, 77 and 1/3%. So that's the chance that no one in your group is going to be chosen at all in the first or second, or to be the first or second contestant. All right, let's look at one more example. Sorry about that. My throat's getting a little scratchy. So a student randomly guesses the answer for each of the multiple choice questions. What's the probability of answering all 3 questions correctly? Well, how many choices do I have? 1, 2, 3, 4, 5. One of these is the right answer. So the probability that you got the first one correct would be 1/5. Same with the second question, and same with the third. Notice these events are independent. The outcome of one event does not impact the likelihood of the other events. So I multiply those together. It's 1 out of 125. So you have about a 0.8% chance of guessing correctly. All right. So here's a testing strategy for you. What if you were able to eliminate one of the answers? What would happen to the probability of getting them all correct? So that's what part 3 or question 3 says. So basically, I eliminate one of the choices. So instead of there being 5 possible outcomes for each question, there's only 4. And the probability that you guess correctly, you get the right one, would be 1 out of 64, or about 1.6%. So notice, by eliminating just one of the answers in each question, it increases the likelihood, even though it's still small, it increases the likelihood that you could guess all 3 correctly. Though, with these percentages being this small, guessing is still not kind of the way to go, unless you could eliminate more of the answers and then guess. Okay, so that's it for section 10.5, I think. I don't think I have any more. I think that's it. Yep, I'm done. All right. So you guys have a good day. And it was good working with you, and I'll see you in class. I'm out with a scratchy voice.